Let's do some examples of a free body diagram, which is a diagram representing the forces acting on an object uh, in an isolated way. All right. So what do? We first see the diagram or visualize the problem. We isolate the object that or objects that we're interested in, and then we represent them with a dot. Since in Newtonian mechanics, objects are treated as dimensional as they're small. And then we use labeled vectors starting from the dot, representing all interactions for our object with the outside world, the forces. Okay, so I just read what I typed in there. So let's start with the first scenario with this. This is known as Atwood machine. All right, and let's assume that the whole thing is at rest. So we all know that if this thing can be at rest only if there is some friction. Otherwise, this will slide down, right? Then we start. We have two objects, right? So we have, let's call this M1 and this M2. So we're going to draw two free body diagrams. So we put a dot for M1 and a dot for M2. And then we start with M2, for example, since it's the easiest one now. So as you can see, there is only a string attached to it, pulling it upward. And then, of course, it's gravity downward. So starting again from the dot, we write Fg2, since has been labeled as M2. And then going upward, we have Ft. All right. And if we know that forces are equal, there is no shame in putting the symbol for equal vectors, all right, in magnitude, sorry. Now we focus on our box or block sitting on the table. Since it's not moving, there has to be friction, as mentioned previously. So we actually might have four forces here, right? We have a contact surface, so we're going to have a normal force. We have the rope, so we're going to have a tension. We have gravity and friction, all right? So we start, and usually if we know that the gravitational force of one is greater than the other, we try our best to show it in there. So here you go. As you can see, I put the gravitational force of the 10 kilogram object slightly bigger than, well, it has to be twice as big as Fg2. The normal in this case are equal to each other because the surface is horizontal after all, and there is no vertical motion happening. And then we have a tension pointing to the right, and this tension here on M1 and this tension on M2, they are the same, all right? And then we have a friction that opposes an attempted sliding motion, so therefore is a static friction. And if they're not moving, it means that these are equal to each other. Again, if we're not sure, we don't have to put those symbols, all right? So there is one example of free body diagram. And here's a typical one. This is a famous double pulley, which means that one of the pulleys is movable, right? This pulley here can move up and down, all right? Recall that we treat the pulleys as massless and frictionless, all right? So we are going to ignore the mass of the pulleys. So here's again M1 and M2. And pretty much if we look at M1, all right, so we put M1 here and M2 here. M1 has one string going upward, the rope pulling it up, so we have a tension. All right, and then we have gravity going downward, so Fg1. We're not sure about their magnitudes because we don't know what the ratio of M1 and M2 is, okay? Now, if you can see here, because we're going to deal with M2 now, the string goes from M1 around the pulley, on the second mass M2, and then up to the hook. All right, so it's the same string. So which means the same tension all over. All right, so which means on M2 there are two tensions, and they have the same value as the tension on M1 going upward, and there is this gravity force of gravity acting on M2 downward. All right. So here's a double pulley free body diagram. Now we go into something that is new probably to grade 12. This is a a banked curve. All right. So you can see this on 401, on race car tracks, but highways mainly for us regular people. All right. So here is a car that we're interested in. Remember, it's moving toward you, toward us. All right. And this car is not sliding down, but is moving like this forward. All right. And the ramp, the curved bank is like this. Okay, so there's an angle theta that this curve has been banked. All right. So here's our car. Here is the ramp. But remember, the car is not sliding down or up. It's moving toward us. All right. So if we were to draw the forces, we don't have to ignore any force for now. But for the moment being, we have gravity pointing downward. I'm using mg for gravity. We can write also just fg, right? It's a contact surface, so there is a normal force. Okay, and what makes a car come toward us is some static friction between. So there is some static friction here between the tires and the asphalt, so allowing the car to move toward us. And if the car is not going too fast or too slow with a perfect speed, that's all the forces that are needed. However, if the car goes slow, then the car, it's attempting to slide downward, right? If there was no friction between tires and the car, then the car would actually start sliding downward. So if that's the case, then there may be some static friction pointing up, right? I'm putting in bracket because this is optional, okay? So it could be there if it's needed, okay, if the car is not going too fast. And if you were to look at the car, what makes it go forward? Well, that's static friction going forward. So static friction has two components here, right? Forward and upward, up the ramp if it's needed, okay? So this is good for uniform circular motion problems, okay? Here's another example, an airplane. So an airplane is negotiating a curve, right? It's turning. All right. So when the airplanes are turned, they are banked, right? So which means now the airplane is at an angle with the ground. All right. So some angle theta. So again, what are the forces acting on the airplane? Well, of course, it's gravity. And then there is some upward force. Let's call it Fn. It's kind of like normal, or all right. So it's some air force, but it's some normal pushing the airplane downward. Okay, and then of course you have air resistance, and then you have the lift, the drag, and all that stuff. But this Fn is a lift force. Actually, let's put it lift. All right. And that's the only two forces acting on an airplane going on a curve. Okay. And the last one, we have modified, again, pulley system. Okay. So again, depending on what kind of information is given to us, let's pretend that there is friction here. Okay. And then there is an actual motion going down, right? So M2 is sliding down, M1 is sliding to the right, but there is friction. Okay, so again, we have two objects that we're interested in. One is M2, and the other one is M1, right? So let's start with M1. M1, it has four forces, and they are gravity, so Fg1, normal, Fn, or Fn1. Then there is a tension going to the right. And since we said there is friction, there is some, and it's moving, there must be some sort of kinetic friction, okay, opposing that sliding motion. All right, and then now we go to M2. So M2 again, there is a ramp like this. So we have gravity. So let's call it FG2. We have some normal because it's still in contact with a surface, but it's at an angle. So FN2. And then we have a tension because there is a rope, which is obvious. FTN is the same as the one on M1 because it's the same rope. But if there is friction, then there is some friction as well opposing the sliding motion of M2 down the ramp. All right. So here you have some free body diagrams of typical situations that we'll deal with in grade 12. All right. Now let's do one that is, I put it there just as an example of some application. This is actually a device for harnessing dumping motion. Sorry, dumping motion energy. All right. So usually think of the car on the wheels, the device for dumping the bumping of the car, the oscillations, okay, or the bumpers in front of the car. If you bump somewhere, it harnesses the energy from the compression or expansion. Or the subway system in London, there is a station that the platform of the station harnesses the energy of all the steps done by people walking the platform. So anyway, to us it doesn't matter, but here we are interested on this object here, okay? So we have a spring on top. So here is my object. We have a spring on top. So we have this elastic force, so we call it Fs. All right. We of course have mg, or gravitational force. Then, as you can see, it's a coil, and there is a magnet underneath, a permanent magnet. So there is some magnetic force. So let's say that it depends on what direction it's moving, but let's say that the force is pulling it downward. So there is some magnetic force as well. All right. So there is a simple battery, if you will, creating energy out of dumping oscillations. All right. And here are the three forces. So we didn't care even what kind of object it is. We just realized, well, there is a magnet, there is a coil, so there should be some attraction or repulsion, whatever the case is. By the way, this is if there is an attraction, okay? But if there is a repulsion, then we have, again, now it depends what happened. Now, if there is a repulsion, what's happening? The spring will compress, right? So now we have the magnetic force going upward, right? And then we have gravity because it's always downward. But now we have the spring force going downward because the spring is being compressed. All right. So if we have a repulsion, right? And here the spring is stretched. Here the spring is compressed. Okay. So please, if you need to get better free body diagram, my only advice that I give you is practice. And any problem that you're solving using Newton's laws, drawing correct free body diagrams, it's 50% of your success pretty much on succeeding in solving those problems.